new equation on the board, and this one looks more complicated than the ones that we've been doing because I've got a sine squared in it. Anytime I see that I've got a trig function squared or to any power or multiplied by another trig function, I'm going to want to try to factor things. So I'm noticing that there's at least one factor of sine in both terms. So I can factor out sine of x. What's left over here would be 2 times the other factor of sine x, and what's left over here would be 1, and that product still equals 0. Now, when you factor, you can always double check your work. If I were to distribute that sine back in, sine x times 2 sine x would give me back the 2 sine squared x. Sine x times minus 1 would give me the minus sine x. Sometimes people forget that minus 1 because they say, oh, I'm taking the whole thing out. But there's got to be something left here so that when I multiply through by the sine x, I get that term back. So if you're factoring out the entire term, there's still going to be a 1 or a minus 1 left over. Now, super important that this was set equal to 0. Probably should have even said that before I factored. Make sure it's set equal to 0 before you factor, because 0 has a very special property. If two things multiply to give me 0, one of them is 0. That is not true of any other number. If two things multiply to give me 5, they could be 1 and 5, so one of those things could be 5, but it could be 10 and a half. It could be -2 and -5 halves. There are lots of things that multiply to give me 5 that aren't 5. But if two things multiply to give me 0, one of those things is 0. So I now know that either sine of x is equal to 0 or 2 sine x minus 1 is equal to 0. And I forgot to write down the directions, but they're all the same. I want to find all solutions in the interval from 0 to 2 pi. The only thing that I'm going to change is once in a while we'll work in degrees. But I'm always going to find all solutions in this interval and then find all solutions. Okay, so I just now have two problems to do. In both cases, I have a trig function equals a number. Now here, I'm going to have to do a little bit of work to get it that way, but I certainly can get this to be just sine x equals a number. Now here, sine of x is equal to 0. That's sort of a special case. I realize that that means that x is going to be a quadrantal angle. Remembering that sine is where the y value on the unit circle is 0, I know that any angle that intersects the unit circle at either of those 2 points is going to have its sine equal to 0. So in this interval, that would be 0 and pi. So I will get for this x equals 0 or pi. Notice 2 pi would also put me here, but we weren't including 2 pi. Sorry, that colon should have been on the outside. So we did want to include 0, we weren't including 2 pi here. Okay. Now here, I would add the 1 over, so I get 2 sine x equals 1. Divide both sides by 2, and sine x is equal to 1/2. So you'll notice I'm now doing the work that we've been doing in previous problems. I just had a little bit of extra work to do first. So sine of x being 1/2 makes it positive. There's definitely going to be a solution in quadrant 1. The other quadrant where sine is positive would be quadrant 2, and I'll have to find my reference angle alpha. No solutions in 3 or 4 because sine would be negative there. Okay. So let's see. If I'm looking for the acute angle whose sine is 1/2, here's my 30, 60, 90, 1, 2, root 3. Looks like 30 degrees, which would be in radians pi over 6. Okay. That's going to mean that my reference angle here is pi over 6. So here, x is pi minus alpha. So that's pi minus pi over 6. That would be 6 pi over 6 minus pi over 6. That would be 5 pi over 6. Okay, so I get 2 more solutions, pi over 6 and 5 pi over 6. Okay. Now, if I want to name all solutions, I can notice that these two are actually just pi apart. So that I can describe as pi times n. Any multiple of pi, we're used to those are the places where sine is equal to 0. These are not pi apart, so I'm going to have to just write pi over 6 plus 2 pi n and 5 pi over 6 plus 2 pi n, where n is an integer. Okay, so that worked out kind of nicely. You'll notice that here we got a nice number, 1/2, that we recognized corresponded to, in this case, a 30-degree angle, or pi over 6. Remember, if we don't get that, we would simply use inverse trig to describe our solutions. So I'm going to put another problem up here on the board. And what I want you to do is try that problem on your own before tuning into the next video. And then we'll look at that one together in the next video. So let's try 2 cosine squared x minus, let's see. Actually, let's make this 3 cosine squared x minus 2 cosine x equals 0. Okay. Give that one a shot. Oh, Rex, I wanted to show you one more thing. So let me show you one more thing. Keep this problem in mind. What we had a moment ago was 2 sine squared x minus sine x was equal to 0. Okay. And we factored out a sine x, and then we had 2 sine x minus 1 equals 0. Sometimes people are tempted to divide by sine x. You remember in the last video I said we can't divide by a variable quantity if we don't know whether it's 0 or not. Here, sine x could be 0, and that's what gave me those two solutions and that infinitely many solutions. If I divided by sine x, whoops, and I was left with just 2 sine x minus 1 equals 0, I'd only be getting these solutions. So, again, you can only divide by a variable expression if you know it is not 0. And very often, if you're solving something and you're using factoring, you're going to have things set equal to 0 so that you can use that 0 product property. So dividing by that expression is not acceptable, okay? Because that's going to it's going to mean that you miss some of the answers. All right, so give this one a shot. We'll tune back in and take a look at it together in the next video.